Good morning, ladies and gentlemen. This is Ben Keyser with Applied Flow Technology, and I would like to thank each and every one of you for joining me in our webinar today, talking about getting ready for a sonic boom. Well, uh, talking about sonic choking with AFT Aero, that is, in compressible flow analysis. And so you're going to learn about how AFT Aero handles that, and one of the difficulties when dealing with compressible flow is when the gas is sonically choked and has reached the speed of sound, typically it's difficult to be able to get the downstream conditions. And Aero does a beautiful job of being able to figure that out. And so you can have sonic choking in your system, and uh, maybe it's really noisy. Maybe you don't want it to sonically choke. Maybe you do want sonic choking. There could be a situation where maybe you're trying to use high velocity gas to clean out the inside of pipes. That would be a application that you want the gas velocity going as fast as it possibly can. And so we're going to focus on sonic choking today. We will see a little bit of the basics and the fundamental equations behind what AFT Aero is using to solve compressible flow. And so let's go ahead and get into it. Just so that everyone knows, the webinar is being recorded. So for those of you who are listening in live, thank you for joining me. You will receive a link later this week so that you can watch the recording of the webinar. And for those of you who are listening into the recording, thank you for listening. All right, so let's go ahead and get started. I'm just going to go ahead and jump right into this. So, what is so special? What is so special about compressible flow? Well, here's our good old mass flow rate equation. Density times cross-sectional area times velocity equals a constant. And in compressible flow, your density is no longer constant anymore. Your density is constantly changing, and your velocity is also changing as the gas expands and flows down a pipeline. And with densities changing, they are a they come along with a corresponding change of velocity, which you'll typically see a highly accelerating behavior of flow inside the pipe, and that acceleration of the gas velocity is nonlinear, and it will exponentially and asymptotically approach the speed of sound. Your density is not only a function of temperature with compressible flow, but also with pressure, and therefore you have to incorporate a energy balance as well as an equation of state. And you can have sonic choking, as we're going to talk about today, and it can become a dominant characteristic of your system. And all of the fundamental thermodynamic equations are strongly coupled together. And if you want to have the correct answers, then you need to make sure that you're properly solving all of the fundamental thermodynamic equations. And when you introduce these characteristics to a more complicated piping system, then that's going to lead to a more complex analysis. And so the way the AFT Aero approaches this is that it's going to solve all the fundamental thermodynamic equations simultaneously. It accounts for real gases as well as heat transfer. If you are a AFT Fathom user, you can turn heat transfer on and off from the system properties window. But in AFT Aero, heat transfer is always turned on and is always being accounted for, which is important for gas analysis. And so that's where we've got our energy balance. And this is a excellent technical paper that was written for Chemical Engineering Magazine back in January of 2000, and it is still directly applicable today as it was then. And that's the nice part about how usually, for the most part, Physics does not typically change very much. Excuse me. All right. So moving on here. These are the five fundamental equations that are being solved in every pipe throughout the piping network. We've got the mass balance, momentum balance, energy balance, equation of state, and Mach number. And so these are the fundamental equations solved inside the pipes. I don't plan on talking about the various marching methods with compressible flow today. If there is time at the end of the webinar, I'll come back to that and get a little bit more detail on how these governing equations are solved. But for right now, if the basic thing that you are able to remember is that there are five fundamental equations, and these are what they are, then you have won half the battle. Just let Arrow do the heavy leg lifting for you. All right, so talking about sonic choking, it happens when the local gas velocity inside a piping system reaches sonic speed, or the speed of sound, or a Mach number of 1. And the Mach number of 1, this is the maximum speed that the gas velocity can go. It's not able to go any faster than that unless you have a very special type of geometry, like a diverging nozzle, and then converges. And so basically, when you have sonic speed, then the flow is going to choke. What that means is that if this is the choke point right here, immediate upstream of that choke point, there's going to be a pressure, a temperature, a velocity, a flow rate, etc. And immediately downstream, there's going to be a sudden drop in pressure, let's say, which may not necessarily be equal to your downstream boundary conditions. DB for downstream boundary. So if the other side of the choke point is atmospheric pressure, then the atmosphere is 14.7 psia if you're at sea level. And so you would potentially have a significant pressure drop across this infinitesimally small shock wave. So that's one of the things that you would see is a sudden drop in pressure as you go through that shock wave. The other thing is, let's say that you are discharging into a pressurized tank. If you're discharging into a pressurized tank and you want to try and be able to get more flow through the system, lowering the downstream pressure is not going to generate any additional flow. So you can try and decrease the pressure inside that discharge tank as much as you want. It's not going to give you any more flow through the system once you are sonically choked. Now, an important note to make is that AFT Aero does not model supersonic flow with Mach numbers greater than 1. Again, you have to have a very special type of component geometry to be able to achieve that, and it's not really application that gets into piping systems very much. So Aero stops at a Mach number of 1, and that is what it does. Okay, so this was the bullet point that I was talking about, where if you were discharging into a downstream pressurized tank, lowering the downstream pressure will not generate any additional flow when the flow has choked. So that would be unfortunate if you're trying to get additional flow. And so there are three different types of geometries that you can sonically choke at. One would be a typical flow restriction, like a orifice or a valve. And then another type of geometry is when you have a flow expansion. So as the diameter increases to a larger value, you're going to have sonic choking potentially across that point. And then finally, you can have sonic choking at a end point of a pipe as it exits your system. Maybe it's discharging into the atmosphere, maybe it's just discharging into a discharge tank. Either way, if you think about how the gas velocity continues to increase exponentially down a pipe, it can hit that Mach number of 1 by the outlet, and that's where you'd have sonic choking. So all three types can happen, and they can all happen in a single system, and you're going to see an example of that here a little bit later on. So how do you calculate sonic choking? Well, it depends upon the local velocity as well as the local flow area. And one of the important things to keep in mind when talking about sonic choking is this vena contracta effect. That is basically your local flow area. So if we have a fictitious pipe here, and inside the pipe, we have a orifice, which I'm going to do in a different color. So let's say this is our orifice plate. What we have here is our diameter of the orifice, d sub 0. That's diameter of the orifice. Okay. Now in green, I have my gas molecules that are flowing through the restriction. And so in order to get through that restriction, the gas velocity increases dramatically. And this is what we have for our vena contracta effect. So for the vena contracta effect, there's a different area for that area of flow. So if this is where the molecules are and they are confined to this particular space, where this is our diameter of the flow area or vena contracta, that's what we're talking about. So throughout this webinar, I'm going to be using the term flow area a lot, and this is what I'm talking about. And so hopefully that vena contracta effect is what we all remember from our fluids days way back. And so that's a very important concept to keep in mind. All right, erase my pretty drawing. So these are important equations, and this is the mass balance equation that is been solved and rearranged and incorporates the momentum balances and equation of state and all that stuff. And as you can see, the mass flow rate is a function of the Mach number. And so this is the function of the Mach number as well as the specific heat ratio, which in simplified terms is the CP over CV value, C sub V or C sub P over C sub V. And so that's our choked mass flow rate, and your choked mass flow rate can be calculated directly. Let's see. All right. Somebody had asked me if I would send the PowerPoint. Yes, I will attach these slides to you all right now. And if you are listening into the recording of this webinar, please email me at benkeiser@aft.com, and I'll send it to you if you're listening to the recording. All right. Thank you for that question. All right. So calculating sonic choking. How do you do it when you are trying to calculate the choked mass flow rate at a choke point when you don't know the pressure and temperature? So if you don't know the temperature and pressure at a point that you're trying to calculate the mass flow rate, you have to iterate. So you can do this manually by hand. The way that you would do this is you would start off by assuming a mass flow rate. When you assume mass flow rate, you solve all of the fundamental thermodynamic equations down a pipe just like you would normally. And if the Mach number equals 1 before the outlet of the pipe, then you would lower the flow rate and repeat steps 1 through 3 until your Mach number equals 1 right at the outlet of the pipe. And so that iteration is how you would calculate the choked mass flow rate when you don't know what the pressure and temperature at the choke is. Give me 1 second. Sorry about that. It's nice and dry here in Colorado, the way I like it, which means that if you ever visit our wonderful state, be sure to drink plenty of water. Gotta stay hydrated, because if you're talking a lot like me, then your voice will get nice and scratchy during a webinar. So stay hydrated. All right, back to it. Who in the world wants to do this iteration? Let AFT Aero do this for you. Now, again, if you're going to do the sonic choking calculations, AFT Aero requires a choked flow area, which, as I mentioned before, I used the term flow area. I also used the term vena contracta. We can also call this a CDA value. And so the CDA value represents that flow area through a choke point. All right. Change my drawing tool. And what we're going to look at here in a few minutes is a really helpful output parameter called the sonic area. This sonic area is simply that previous choked mass flow rate equation, which is rearranged for area, and this is the area when you are sonically choked at a Mach number of 1. And so when you rearrange that choked mass flow rate equation, you can calculate your sonic area. And the reason why this parameter is helpful is because it can help you determine your margin between if you are sonically choked or if you are not sonically choked. And this is a picture that I drew a long time ago. And the key thing is to pretend like this is a overblown orifice plate. So think of an orifice plate that I just made very, very long to illustrate these cross-sectional areas. So if this is a orifice plate, what we have is our flow area. So this flow area, that is our vena contracta, all right? If the sonic area was calculated to be less than your flow area, then you're not going to have any sonic choking. You'll be remaining subsonic through that restriction. However, if your sonic area is greater than your flow area, then you will have sonic choking. So when we're starting to look at the next example here, keeping this equation in mind for determining your sonic choking, this is how we're going to figure out if we're going to be sonically choked or not. All right. Note that if you want to avoid sonic choking, make your flow area or your vena contracta or your CDA value larger than the sonic area. And remember, this is a directly calculated parameter in the output that you'll see here in just a moment. All right, so what we're going to do now is we're going to take a look at a very simple example for flow through an orifice plate. Okay, so when we have flow through an orifice plate, there's a restriction. It is possible that you might sonically choke across the orifice. However, we also have a endpoint into a discharge tank, which is at atmospheric pressure. So if we are starting at 250 psig and we are flowing through a couple of 2-inch diameter pipes and an orifice, if we're going from 250 psig to 0, that's a huge pressure drop over a really short system. And so highly likely, when you look at the velocity in this pipe right here, there's going to be a dramatic acceleration in velocity as we approach the exit into the discharge tank, and we will probably have sonic choking as the flow exits the pipe. So we're going to take a look at that in detail, and we're going to review a few scenarios with this. And so here is, if you remember, we need that CDA value to calculate the choked mass flow rate. So if I go back a few slides, if I go back to this equation right here, this area, that's your CDA value for a restriction. And that's why it's important that you have a CDA value so that arrow can calculate if you're choked. If you don't have a flow area that's specified, then what AFT arrow will do is it's going to assume that the area of the diameter of the orifice is your, essentially what your CDA value is. So it's a first approximation. If it finds that you might be choked based upon that orifice diameter, you'll see warning messages that tell you so. All right, let me go and open up that example. All right. Okay, so here's our orifice plate, and the gas that we are modeling is steam, and we have our inlet tank at a pressure of 250 psig, temperature 500 degrees Fahrenheit. We are then discharging out into a discharge tank at atmospheric pressure 0 psig. Now, if you notice, I did specify a temperature here. This temperature actually does not matter. That temperature is not used for calculations. The only way that it would be used for calculations is somehow if I had made a mistake and I accidentally made this pressure larger than my supply tank to where I would have reverse flow through the system, that's where the temperature would be required. So one thing I want you to keep in mind is for your discharge boundary conditions, the temperature is only going to be used if this discharge actually starts supplying flow. All right, otherwise you can make that temperature whatever you want as long as you're flowing in the proper direction. Doesn't matter what it is. All right. So we got that. And then if we take a look at our input for our pipes, this pipe is 2 inches in diameter, 10 feet long. And the second pipe is 20 feet long. So again, I've got a 250 PSI pressure drop from the supply tank to the discharge tank, and 250 PSI over 30 feet total of 2-inch diameter piping and an orifice. That's a major pressure drop there. So right now, when I start with this flow model, to keep things simple, with our orifice plate here, I'm just going to use a basic K factor for a subsonic loss, and this is my area of the orifice plate. Notice how I'm leaving this CDA value blank. So for right now, I'm not going to really pay attention to what the sonic choking might be through the orifice. So let's just run this as it is based upon the K factor of 10. So when I run this, take a look at our results. And what I'm going to do is I'm going to focus on the results in this fashion. All right, let's rearrange the output a little bit. So remember that sonic area that I was talking about? That is this parameter right here. So I'm going to move that up near the top so that it appears first. So going to rearrange our parameters a little bit. So I'm going to have my sonic area, my mass flow rate, my pressure drop, and then I've got my pressures. I'll put these pressures in terms of PSIG. We'll keep the temperatures in there, but I'm going to take off the enthalpy parameters. There we go. That's a little bit nicer. Okay, so we have a flow rate through the system of 4.6 pounds per second, and our sonic area at the orifice is calculated to be 1.37. Do we have sonic choking in our system? Well, yes, we do. If I go to the sonic choking tab, you can see here that we have sonic choking at the discharge tank. So the gas velocity for this pipe is increasing significantly, and we're going to reach a Mach number of 1 at the discharge tank. So let's take a look at the pipe results here. So if I look at the pipe results, we see that we have a Mach number of 0.24 to a Mach number of 0.25 in pipe 1. So it's a very small increase in Mach number. Next, we have a Mach number of 0.4 at the inlet of pipe 2 and 0.99, basically that's 1, at the outlet. So we have a very, very high Mach number at the outlet where we are sonically choked. But what's really going on inside this 20-foot long pipe here? Well, if you were to, I'll reset the windows here. If we were to take a look at the axial points here, I can expand pipe 2 and I can right click on any of these cells and I can do a quick graph. And this shows you how the Mach number increases down the pipeline. And so it starts to increase dramatically in the last few feet. So that's the nature of compressible flow. All right. Now, what we're going to do here is we're going to do a little experiment. We're going to try and figure out what the discharge pressure of the tank needs to be where we just start being sonically choked. So initially, this is at 0 PSI. PSIG. Man, my handwriting with my mouse is just not on it today. So what we're going to do is I'm going to increase the pressure of the discharge so that we can try and see when we start becoming sonically choked. And I'm going to put my mass flow rate first. There we go. All right. So here, I'm going to leave my orifice alone, not touch that. and I'm going to open up my discharge tank, and I'm going to set this pressure to 50 psig. So if I set the pressure of that tank to 50 psig, and we look at our orifice plate, look here, we've got 4.65 pounds per second. So this is the thought experiment I was talking about, where if we have a discharge pressure of 50 psig and we are sonically choked at the tank, which we are, if I wanted to try and lower the pressure of the tank, I'm not going to be able to get any additional flow. So if I wanted to reduce this down to 25, this would increase the pressure drop in the system to be a bigger driving force for flow. But look at that, no more flow with lowering the downstream pressure. That's the nature of sonic choking. So I left this off at 25, or previously I started at, or I did 50 psig. Let's put this up to 100 psig. So if I put this up to 100 psig and I click OK and I rerun this, well, would you look at that? I have a slightly different flow rate, and look, no sonic choking tabs. So there is no sonic choking in this system. Now, the gas velocity is getting close to reaching sonic speed, but it's not quite there yet. If I was to look at my, if I was to do a graph of the Mach number, let's change this to Mach number. Here, this is what we see at the outlet. So it's not at a Mach number of 1. So that's what we have going on there. Now, let's start decreasing that pressure, because what I know is at 100 psig, I'm not sonically choked anymore. So what I'm going to do is I'm going to start from 100 psig, and I'm going to start going down in pressure to try and see if I can get additional flow. And I'm going to try and see how low can I drop that pressure of the discharge tank in order to increase my mass flow rate. So let's set this pressure now to 80 psig. So if I set it to 80 psig, we have sonic choking again. So it's the same 4.646 pounds per second. So I know that I'm going to call it the critical point where we start sonically choking is somewhere between 100 psig and 80 psig. Within this range is that pressure where I start to sonically choke. And I'm trying to figure out where that is, because that's going to show me what the pressure in the tank would need to be to give me my maximum amount of flow. So let's bump this back up. Let's put it up to 90 psig. If I go to 90 psig, will I still have sonic choking? And I do not. And so I don't have any sonic choking messages, and I have 4.64 pounds per second. And so this is slightly lower than the choked flow mass flow rate, which was 4.646. All right. So now I know that somewhere between 90 and 80, that's where I'm going to have that critical pressure where I start choking. Not critical pressure as in critical pressure and critical temperature. I'm just using the word critical to emphasize that's the pressure where we first start to sonically choke. So now if I change this back down to 95, or change it up to 95, are we still sonically choked? And we are not. No choked flow rate mass, no choked flow rate equation. So the somewhere between 95 psig and 100 is where we're going to see sonic choking begin. So, so I'm going to set this down to 92. No sonic choking, so let's lower the pressure again. I think it was actually between 90 and 80. So I went in the I went in the wrong direction. Let's try 85 psig. It's somewhere between 85 and 90. So here, if I set this to 85 psig, we have our sonic choking again, 4.646 pounds per second. So that critical pressure is somewhere between 85 and 90. Let's set it at 87. So if I set it to 87, and I rerun the model here, I still have sonic choking. And let's bump this up to 88. I've still got sonic choking. Let's make this 89. All right, so at 89 psig, I have no sonic choking, and my mass flow rate is 4.643 pounds per second. So that's the point where I go from subsonic flow to sonic flow. All right, so if I go back to my graph results and I replot that Mach number, here you can see that we're just about up to a Mach number of 1. Okay, so between 89 and 88 psig, that's where we have that critical point where we start sonically choking. So I went from 89 psig, where I was not sonically choked, down to 88 psig. And I am sonically choked. So that's a difference of 1 psi. So in a difference of 1 psi, we went from subsonic to sonic in 1 psi. And so it very well can make a significant difference. And so this is what I like to do to help illustrate the point of, if you're trying to increase the flow rate of your system, lowering the downstream pressure is not going to help you get additional flow when you are sonically choked. So what this means is that, let's say it's 88.5, okay? Any pressure inside the tank that you set that tank pressure to, from 88.5 psig all the way down to 0, any pressure that you set it here is not going to generate any additional flow. Your Mach number stays the same in that whole range of pressure. So that is where we have a shock wave. So when you are setting this back to 0, what's the actual pressure at the outlet of the pipe? Well, let's look. If I set this back down to 0 psig, like we're discharging into the atmosphere, this is where it's helpful to look at the pressure inside the pipes. So let's look at pipe 2. We have the stagnation pressure at the outlet of pipe 2. These are all in PSIA units. Let's change them to PSIG really quick. And I'm going to remove a parameter here. So we'll make these all be PSIG. All right, so look at this. This is interesting. Our stagnation pressure at the outlet of pipe 2 is equal to 88.27 PSIG. Well, I knew that somewhere between 88 and 89, somewhere in that range is where I start to sonically choke, where the Mach number equals 1 at the outlet of the pipe. So here our Mach number equals 1, and that critical pressure right there is 88.27 psi. So that's what this means. Your pressure at the pipe is 88 psig, and then immediately downstream, once it flows into the atmosphere, there's a pressure drop of basically 88 psi across your shock wave. And so that is our choked pressure drop. And so you have a very, very thin interface between the outlet of the pipe and then the atmosphere. And across this extremely small boundary, we're going from basically 88 psig to 0. And that is your pressure drop across the shock wave. So that's pretty significant. You're just throwing away 88 psi from your piping, and maybe that's good, maybe that's bad, but it is what it is. And so you're not going to get any more flow if you are trying to if you're decreasing your downstream pressure from this value and lower. Now, let's start looking at the sonic choking conditions of the orifice. All right. So here in this scenario, as you saw, there's no CDA value, and also there's no warning messages telling me that because of the diameter of my orifice, the flow area might be larger where I might have sonic choking. It's not telling me that. So this is where we're going to try two different scenarios. We're going to incorporate a CDA value to see where we have sonic choking across the orifice. So the way that you would start that off is we're trying to figure out where that margin is. So if I go back to this picture right here, I'm trying to figure out how much margin do I have between choking and not choking. So this is my sonic area that is calculated for me by AFT Aero. So if I go back into Aero here, and let me do that and do that. There we go. So here's my sonic area, 1.377. What we're going to do is we're going to try and make our CDA value 20% larger and 20% smaller than our sonic area. And we're going to see if that makes an impact on our results. So here's our 20% higher scenario. So basically we took that 1.377 value and we multiplied it by 1.2. So this is a CDA that is 20% larger than our flow area. So if you remember, if your flow area is larger than your sonic area, no sonic choking. So we should not see choking. Let's see what happens. I run the model. I do have sonic choking, but it's only at the discharge tank. This is what we were just doing where we had sonic choking at the end point of the system, and there's no sonic choking across the orifice. So here, everything is the same. You can make that you can make that CDA value basically as large as the diameter potentially and of the orifice, and you wouldn't see any differences in results. However, if the sonic area, I'm sorry, if the flow area is smaller than your sonic area, then you will have sonic choking. So here, if I load this particular scenario, this CDA value is basically the 1.377 square inches times 0.8 or 80%. So we have a smaller flow area than our sonic area. So that's comparing our flow area to the larger sonic area, and we will see sonic choking and potentially a different mass flow right now. So when I run this, well, look at that. I now have sonic choking at the orifice and the discharge tank. So here, because my vena contracta is different and it's larger than the sonic area, I now have new conditions where I have a new mass flow rate and a new sonic area. So this is where the orifice starts impacting things. And this is where you can play with your CDA value. So if you want to try and make this flow a little bit larger, if you want to increase your flow rate, maybe you can try increasing your CDA value, your flow area a little bit. Now, it has to be somewhere between 1.1 and 1.377. So let's make this 1.25. So if I went from 1.1, that gave me a flow rate of 3.76 pounds per second. I'm going to go to a larger flow area, but it's still sonically choked. I'm going to see if this helps give me some more flow. So remember 3.76, all right? So we got 3.76. We're going to try and see if we can beat that flow rate. And we do. So we went from 3.76 up to 4.2. So that is another parameter that you can tweak if you are sonically choked across a restriction and you still want to try and squeeze a little bit more flow through it. And so if you are sonically choked across a restriction like that and you want more flow through your system, try and see if you can increase that CDA value or the flow area to where it's a little bit larger, and maybe that might be able to give you more flow. Now, I don't know how exactly you would do that. It depends on things that you're able to change. You know, if your diameter of the orifice stays fixed, you know, maybe it might be something like, you know, if you can trim the corners, you know, maybe instead of doing sharp edged, maybe you do, you know, a bit more rounded. You know, maybe this is what can help increase your flow area a little bit. Because if you're making those more rounded, you might have a little bit bigger of a space for that flow area than when it was sharp edged. So that might be something that you can do to help increase your CDA value to get more flow rate even while remaining sonically choked. All right. Now, one thing that is important to mention is that if you are in sonic choking conditions, there's a certain point where when you change your CDA value, if I make this equal to the sonic area that I got before, 1.377, if I go larger than that, just like this scenario, it's not going to make any difference at all, because I would not be sonically choked at the orifice anymore. I'd only be choked at the tank. So when you have sonic choking in your system, one way to help generate more flow would be to increase the supply pressure. So if we increase the supply pressure, that can help generate more flow. So if I take this up to 300 psig, we still have sonic choking, but we have a higher flow rate. So you can't drop the downstream pressure once you're choked to get more flow. You might be able to play with the CDA value a little bit, but ultimately, if you want more flow in your system, try increasing the supply pressure, and that can help you with that. Now, let's talk about how Arrow handles sonic choking when you have multiple choke points. So this was very similar to what we saw before, where we had an orifice and an endpoint. Okay, in this particular system, we now have another geometry, which is an expansion. We're going from 6 inches in diameter to 18 inches in diameter. And so when you have that situation, you can potentially be sonically choked. And in fact, you do in this particular scenario. So here's your first choke point at the expansion. Your second choke point is at the orifice. Your third choke point is at the discharge. So what's actually happening here? Well, wherever the first location of your choke point is, that's what sets your choked mass flow rate, M.C for choked mass flow rate. So keep in mind that in a flow path, the first geometry that you have sonic choking, that's what sets the flow rate through the rest of the system, because mass cannot be created or destroyed. And so here we know that the flow rate would balance. So what we're going to talk about now is how AFT Arrow handles this type of behavior. So what it's doing is it starts off with these boundary conditions at the inlet of the system. And we use the marching methods, which I didn't get a chance to talk about today, but we use the marching methods, which are talked about in that Chemi magazine article on compressible flow that I referred you to in the PowerPoint. It'll talk about what the marching methods are. Basically, it is employing the 5 fundamental thermodynamic equations to solve for all your pressures, temperatures, flow rates, velocities, densities, etc. So we start with our inlet conditions and we start marching down the pipe. And as we march down the pipe, we calculate all the pressures, temperatures, velocities, etc. We are making sure that the mass balances, momentum balances, and energy balances at each computation station along the pipe as we march along. Then we round the elbow here and we keep marching along down the pipe. And if you remember, the Mach number is going to be constantly increasing because your velocity is increasing due to your compressible flow. So when that Mach number increases, we get to a expansion here where, look at our Mach number. It's at 0.982. So that is where we find out that our gas is accelerated so much up to this expansion point. That's where we're going to have a sonic shock wave, which is a discontinuity in pressure. So after we choke, the question is, how do we calculate the conditions everywhere else? Well, that's where we basically start with the discharge boundary condition and we work our way backwards. So here's how AFT Arrow does this. Is we essentially break up the piping system into pseudo boundaries. So here we know the inlet conditions of our supply tank, and we march up to the first choke point at the expansion. And again, the first choke point in the series flow path, that's what sets your choked mass flow rate. So we know the mass flow rate through the rest of the system. We know M dot. Also, we know that across a shock wave, the mass has to balance, the energy also has to balance. Okay, so we know the mass and the energy across that shock wave. So basically, what we do is we break apart the system and we create a small pseudo subsystem where we put a pseudo known flow boundary right here. So basically, it's like we're taking the model inside the code and we're putting a assigned flow with a known energy condition at that point. And we start marching downstream again. But here's the thing is at this orifice plate, we have a hiccup. Okay, so we have a discontinuity where we really don't know what's going on inside that pipe yet. That's where we actually start from the discharge boundary and we work our way backwards. All right, so we know the marching methods, we know the pressure right here, and we know the flow rate and the energy across this boundary because again, it has to be able to balance. So we start working our way back up, calculating what the pressures and flow rates and temperatures would be up to this point right here, which is downstream of the choke, and then we can keep working our way backwards. And so it is highly iterative, very much so, to ensure that the mass and energy and momentum is balancing all throughout the network there. But that's how Arrow is doing it inside the solver. Is it starts with the inlet conditions, it figures out what the first choke point is, and then we impose a known flow and known energy at the pseudo boundary here and here, and then we start working our way backwards from the discharge boundary condition. And so if you were to graph what was happening for this particular system, I'll show you what it looks like. So let me open up that model. Let's see, I need to find where it is. Let's see here. One moment. All right, so here's our system. We've got the 6-inch diameter piping, and it's very short, 3 feet. So we go 3 feet, and then we expand into the 18-inch diameter pipe. So this very well could be a condition that you have. So 300 PSIA, and when I run this model, here's our sonic choking. So we can see that we sonically choke at the area change, the orifice plate, and the tank. And so if you look at this graph, we're going to make some plots here. So we'll take a look at the Mach number, and we'll do the, we can also do velocity, and we'll look at pressure and temperature. And so let me, the pressures and temperatures that we're looking at here are static pressures and temperatures. All right, so what I just did there was I plotted the Mach number, as well as the velocity, and then the pressure and the temperature. So here we have our first choke point. This is our area change. And as you can see, we basically get to a Mach number of 1 at that location. And then immediately downstream, the thing to pay attention to is it becomes subsonic again. So that's one of the things that you'll see with compressible flow is that downstream of the shock, immediately you'll be subsonic again. There's very small change in Mach number in this part of the flow path here. And then we get to the orifice plate. Here's our orifice, and we see that we have a dramatic increase in Mach number, and there's a discontinuity. But why do we not see a Mach number equal to 1? Well, the reason why is because the Mach number equals 1 inside the orifice plate. This is a graph of the Mach number in the pipes. Okay, so here we see a high Mach number inside the pipes, but where it actually equals a Mach number of 1, that's going to be inside the junction itself. So if I go back to the output window and I look at my orifice, there's my Mach number of 1 at the orifice plate. And then immediately after the orifice, we are subsonic again as we flow towards the exit, and then we have our Mach number of 1 at the outlet of the system, and we're sonically choked again. So this is where doing the graphing in AFT Aero for compressible flow is a little bit more fun, because you can see here that the pressure profiles and the temperature profiles are a little bit more interesting. They're not linear, and they can have some very strange and odd behavior. Keep in mind that I mentioned how Aero is always doing heat transfer. Even if you have adiabatic pipes, your temperature is still changing all throughout the system. So keep that in mind as you're dealing with compressible flow. And then you'll probably want to account for convection, different things like that. All right. So that is basically what I wanted. Oh, there's a couple more quick things I wanted to mention here with the compressible flow. So there's 2 pressure loss mechanisms. So you've got your K factor, which is your regular K factor for subsonic losses, like the K factor for an orifice plate. And then there's sonic losses. Sonic losses is defined by that CDA value. So the thing is, if you're subsonic, you're going to see a loss based upon the K factor. If you are sonically choked, then that K factor doesn't matter. You're going to see a pressure drop due to the CDA value for sonic choking. And it's important to point out that these 2 pressure loss mechanisms cannot happen at the same time. Either you're going to have a subsonic loss, or you're going to have a sonic loss when the Mach number equals 1. And then one other thing to keep in mind just on valve modeling with AFT Aero is that the CV calculations are more complicated than in incompressible flow. They deal with this XT parameter as well as the FLFD parameters. And so just so that everyone's aware, AFT Aero uses this standard for the flow code. This is an old outdated date. We are using the most recent. And so this is just an old version of that standard. But that's what we're using to calculate the flow coefficients across valves in compressible flow circumstances. So it's more complex than in liquid piping systems. All right. Well, that is what I had for today. And I want to thank all of you for joining me. and hope that you enjoyed the webinar. And if any of you have any questions, feel free to contact us. And again, you can email me at Ben Keiser, that's BenKeiser at aft.com. Feel like John Madden here. No spaces, no periods, no dashes or anything like that. Just first name, last name at aft.com. All right. Thank you very much, everyone. Take care and have a wonderful rest of your week.